In this lecture, we're going to talk a little bit about multiaxial fatigue. And probably the first thing we ought to address is, what does multiaxial mean? And it kind of depends on the context of the situation and who you're talking to is kind of the answer to that. But for uniaxial fatigue, is what we've been focusing on, we typically have a uniaxial stress state, and then we compare that stress state to enter that into the SN curve, or we use that to calculate strains, and we use that strain range to enter that into the strain life curve and so forth. So the way I usually talk about multiaxial fatigue is when we have a multiaxial stress state. Now, most fatigue failures still initiate on the surface of the component, even if you have multiaxial stress states. So you may have two stresses, two normal stresses, and a shearing stress. Sigma x, sigma y, and tau xy. Now, if you've been through mechanics of materials, you know about how different values of these stresses can alter the principal stress directions. And an issue with fatigue is that these are now time histories, and they all may be different histories in time. So they don't have to be in phase, they don't have to increase and decrease at the same time. And so we can get some very interesting material and cracking behaviors due to this more complicated state of stress. If all of our stresses were uniaxial, like in the first picture, then in this case, we would pretty well expect the cracking plane to be perpendicular to that stress direction. The initiation plane might be at 45 degrees to the axis, and I'll also point out that that could be a 45-degree in plane or a 45-degree out of plane initiation for maximum shearing stresses and strains. Now here's something that's kind of interesting. Even if we have a uniaxial stress state, we end up with a multiaxial strain state. What I mean by that is, if we were to look at a cube of material and had it subjected to just this stress in the vertical direction, we would get a strain in this direction. Maybe we can call that epsilon y if we would like. But we would also get strains in these directions as well. We would get an epsilon x and an epsilon z. Of course, this would be minus nu times epsilon y if we're in the elastic range, and then minus nu times epsilon y again here for this one. Now, even though there's several strain components, these are dependent, so I guess you could say there's one primary strain. But when we have complicated stress blocks like this, we could have even more complicated strain blocks. Now, another thing that people also often throw out for multiaxial, and they'll use this word kind of interchangeably with all these different scenarios, is they'll say multiaxial loading. And this is the term you have to be really careful about, because depending on the context, the meaning may vary. So some people say multiaxial loading, and what they have is a tube, and maybe they have tension and torsion. Okay, sure, that is multiaxial loading. We have a load here, an axial force load, and we have a torsional load. So what they mean by that is more than one load. Now, does that mean that we have a multiaxial stress state? Well, many times it does. In the case of tension and torsion on a tube, you would get a multiaxial stress state. Let's take a look at another situation where maybe we have a plate and we have an axial force and we had some sort of shear force that we could put on this plate. So we have two loads. And it's in equilibrium and everything. There's no problem there. Well, in certain parts of this plate, we would have a multiaxial stress state. But in other parts of this plate, we would have a uniaxial stress state. And even if it's anywhere along the edge of this hole for a thin plate, every point along that edge of that hole would have a uniaxial stress state. Okay, the radial stress would be 0 because we don't have any way to sustain a stress through this way. The shearing stress would be 0 because we don't have any way to sustain a shearing stress because this is a traction-free surface inside of here. But if we were to look at this, we would have a kind of a theta stress that is tangential to the surface of that circle, and that would be non-zero. But that's still a uniaxial stress state. So we have to be kind of careful and specific and have an understanding of what the what someone means when they say they're looking at multiaxial loading. So let's just put it this way: multiaxial loading could result in a uniaxial stress state. All right, well, let's say we have a situation where we have a multiaxial stress state, and we do want to find out how that influences the fatigue behavior at that location. There is some terminology that you should know that goes along with multiaxial stress states. And since we're talking about fatigue, all of these can be time histories of these different stress components. The first case is what I call is what is known as proportional loading or proportional stressing. Again, that's another term. I will almost always say proportional loading, and as far as the stress state goes, what is meant then for the stress state is that we have proportional stressing. So if we were to take a look at one of these, like the sigma x as a function of time, we could separate that out into some function of time times a scalar. And for sigma y, we would have the same function of times a different scalar. So maybe we could say this is scalar x, maybe this is scalar y. And likewise for tau xy, it's a function of time, that same function of time times another scalar for the shear stress xy. What would this time history look like? Let's see if I can draw this. So maybe our sigma x history looks like a nice sine wave. Well, our sigma y history may not have the same amplitudes. Okay, but it follows the same function in time. And likewise, trying to draw a sine wave here. For tau xy, maybe it's steep, but it crosses 0 at the exact same point. I'm trying to show it crossing 0 at the same point, and it peaks at the same point in time as all the others. So all of these are a sine wave, they just have different amplitudes. It doesn't have to be a sine wave, it could be whatever waveform you have. It could even be variable amplitude loading, but those variable amplitude loadings are all just scaled functions in time from one another. Many times we look at a phase plot to describe what proportional loading looks like. And in the phase plot, it's usually for tension and torsion. If we were to plot sigma on this axis and tau on this axis, then the phase plot would be a line that goes back and forth as these amplitudes increase, and they go in proportion to one another. Let's contrast that to something that is non-proportional, and basically anything that is not proportional is non-proportional. In mathematics terminology, you would talk about a linear relationship or a non-linear relationship. Proportional and non-proportional basically means the same sort of thing. Now let me clean this page off and I'll make another graph. All right, so non-proportional would be we have all different functions of time. Okay, so maybe sigma x does something like this. Okay, maybe it's still a sine wave type function. Maybe sigma y has an increased frequency. And maybe tau xy is just all over the place. Variable amplitude. Well, these would be examples of non-proportional histories. In as many ways that we can think up time histories, those are the ways that we could have non-proportional histories. Now, in typical practical situations, oftentimes you'd have proportional loading. Sometimes you would have non-proportional loading. An example I like to give is a light pole. I think we've talked about this already. A light pole that's bending in the wind, and it has a superimposed higher frequency torsion on top of that. You can have multiple frequencies of torsion, multiple cycles of torsion in the same as an overall bending cycle. That would be an example of non-proportional type loading. Of course, variable amplitude loading in different situations that you can have in different types of vehicles, whether they're aircraft or ground vehicles or trains or whatnot, you can get different types of non-proportional kind of loading. Now, from a testing environment, there are some commonly tested proportional and non-proportional type loading paths. Now, if you wanted to do multiaxial research done in the lab, you'd have to use a multiaxial testing machine. Testing machines usually tend to come in two varieties. The most common variety for multiaxial loading is a tension torsion testing machine. In a tension torsion testing machine, you tend to develop an axial load and some sort of shear from the torsion. So you have an axial stress and a shearing stress. So we can call this sigma and tau. It is possible with additional controls and test configurations to get a stress in the hoop direction. If you did internal and or external pressure, you can vary the hoop stress, so you could get two directions of sigma and a direction of tau. We're going to see a little bit later when we look at a paper of Daryl Sosey's how this can influence the cracking behavior in a material when you add that additional hoop stress to it. There's another type of testing machine that's a little bit more rare, but it does exist. There is one in which you can apply biaxial loading. So you can apply a force in the vertical and a force in the horizontal direction on a specimen, and then you can get fatigue that way. It's a little bit more common in composite materials, but it can also be used in metals as well. Let's take a look at tension and torsion. We'll just keep it as two components of stress for right now. Okay, so you might look at this and say, well, I know I can change my sigma and I know I can change my tau, but is there a way that I can get an equivalent amount of sigma and tau? And the answer is yes, there actually is. If you're testing a metal and it tends to follow the von Mises yield criterion, I'll write down the von Mises yield criterion in full, and then I'll simplify it for tension torsion. Von Mises yield criterion looks like this: 1 over the square root of 2. We have the differences among the normal stresses squared. So sigma x minus sigma y squared, sigma y minus sigma z squared, sigma z minus sigma x squared. And then we have 6 times each of the shearing stress components squared. All of that to the 1/2 power, and then we divide it by the square root of 2. For tension torsion, this simplifies down. We end up with a sigma squared and another sigma squared, and then we have a 6 tau squared term in here, where maybe sigma y represents the sigma and tau represents the tau xy in that formula. And I need my square root right there. All right, so if we take a look at this, we end up with 2 sigma squareds. We have 6 tau squareds. I can take this and bring it inside of the square root. And so if I wanted an equivalent stress in tension as it is in torsion, well, every sigma is worth square root of 3 tau. So let's see. Let me write it this way. So if I picked out a level of stress of 100 megapascals in tension, then the equivalent shear stress I could find out by taking the square root of 3 times tau. Right, so maybe the other way is a little easier. So if tau was 100 megapascals, then the equivalent normal stress would be square root of 3 times 100. So what's square root of 3? About 1.57, I think. I've got my calculator, I can check that out. 1.73. Okay, so what that's saying is the shearing stress is in a way more damaging than the sigma, damaging from the sense of contribution to plasticity or the equivalent stress. So the von Mises stress is used usually as a yield criterion that determines plastic flow, but it goes beyond that, and we'll talk a little bit about multiaxial plasticity here in just a moment as well. So if I were to show on a phase plot, let me make a new slide here. On a phase plot, first I'll draw my stress state. I would usually have sigma, say on this axis, and then the square root of 3 times tau on this axis. A proportional loading path would go something like this. Or in phase proportional stressing. Now any kind of waveform that has the same function and time for sigma and tau will give you this type of path. Most frequently in testing machines we use sinusoidal waveforms. So this would be a path that would look like this for sigma, and then the proportional path, the amplitudes may be different, but this would look like this in tau. And if we wanted the equivalent, then we would scale these to the same value. This would be called in-phase loading. Now by shifting the phase, we can have out-of-phase loading, and then the most common out-of-phase loading is a 90-degree out-of-phase path. And again, on the axes of sigma and square root of 3 tau, they would have the same amplitudes, but they would be 90 degrees out of phase. Let me see if I can try to draw a 90-degree out of phase. So 180-degree out of phase would be completely separate amplitudes, but I'm going to shift this over. It's kind of like a cosine wave. I'll try my best to sketch that. So this would be the sigma in the square root of 3 times tau over here. And in this case, it would form a perfect circle in the phase space. Again, known as 90 degrees out of phase. Sometimes you see the abbreviation OOP, loading. Now, in addition to talking about stresses, we can also do the same thing with strains. Now, the coefficient on the shearing strain is not the square root of 3, but there is a similar coefficient that goes in front of that, and we'll see what that is a little bit later. We're going to take a look at some papers where people have done multi-axial in-phase and out-of-phase type loading. So once you get used to looking at phase plots, they can really convey a lot of information in a compact way. So we have a proportional loading in the first path, and if it's 45 degrees on those axes, then you have equal amounts of sigma and tau contribution to the equivalent stress. If you start changing the angle away from 45 degrees, then you have more contributions of sigma or tau respectively as that line tilts up or down. Now for non-proportional loading, there's many other paths. 90-degree out of phase is one example. What you can do is you can set up an Excel spreadsheet and you can try your own sinusoidal, non-proportional, and proportional paths by changing the phase angle, by changing the frequency, and you can have all sorts of interesting type of loading paths. And it's not just these circles that plot in phase space, but you can also plot boxes or sawtooth patterns and so forth. Now going along with this is Moore's circle for time histories. So you're probably familiar with Moore's circle if you're taking this class. But in Moore's circle, when we have a multi-axial stress state, and it could be tension and torsion, or it could be for plane stress, 2 sigmas and a tau. Let's just kind of stick to this for right now. Maybe a sigma and a tau. Then we would have, for a given value of sigma and tau, we would plot our, let's see, on our sigma plus tau axes this way. We would have our sigma and tau point. We would have the average, which would be, in this case, sigma over 2. And then this point over here would be 0, minus tau. And then we would have a circle. Let's see if I can maybe use this tool to draw a circle. Got pretty close to getting my diameter right. And if we have proportional loading, what we would see is if we were to plot this Moore's circle as a function of time, this Moore's circle would increase and decrease in size as the loading progressed. So again, if I had, we can see this dynamically, as the stresses get larger, circle gets larger, and as the stresses get smaller, circle gets smaller. So it would tend to increase in size as a function of time. This is a very handy way to think about Moore's circle when you're dealing with fatigue histories. Now for proportional loading, oops. proportional loading, the principal axes, the principal directions of stress remain unchanged. So if you remember, we usually call this point sigma p1, comma 0, and this point sigma p2, comma 0. Now those values will change as the circle gets larger and smaller, but the angle here on the more circle 2 theta p remains the same. So for proportional loading, the principal angle in the material would be theta p, remains the same. Now from a fatigue perspective, this is kind of handy if that's the case, because your cracking orientation, all the main damage, if you think of the principal stress causing the most damage, all of that's occurring on one plane, or your maximum shearing stress if you're looking at more of initiation type loading. For non-proportional loading, the principal stress directions can change with time. And this gets to be a little bit more challenging when you think about what's happening in the material. So if we were to take a look at a stress block and the principal stress directions at one instant in time were off in this direction, and cracks were forming perpendicular to the maximum principal stress here, or they wanted to form, or there was damage occurring to that plane, then at another instant of time, the principal directions change down this way. Let's call this T1, and over here, maybe this is theta p T2, and then the damage was occurring on a plane that's in this direction. Okay, so these are some of the challenges that can happen when we have non-proportional stressing, non-proportional fatigue occurring. And this happens under multiaxial situations. Of course, if you only have uniaxial, then everything is fairly redundant. It's just fixed in its directions. But by adding these extra stresses and adding these things that can change as a function of time in different directions, we can have some interesting things happen to our material. All right, so I wanted to give a little bit of background on what we mean by multiaxial fatigue and multiaxial stressing. So there are a couple ways that people have tried to handle this situation. Some of them work for proportional loading only, and some of them work for proportional loading most of the time. And we're going to talk about those. And then later on, we're going to talk about something called a critical plane approach to multiaxial fatigue, which is a little more physically based and seems like the most sound of several methods. All right, so let me clean this off, and we'll talk about ways to handle multiaxial stress states. All right, so we have our multiaxial stress state, sigma x, sigma y, and tau xy are all changing with time. Let's not get into the details about whether it's proportional or non-proportional yet. But we've talked about using the von Mises stress as an equivalent stress. And so if we have this plane stress state, even if we don't have a plane stress state, one way we can handle this, maybe we can handle it this way. Let's talk about the advantages and disadvantages. And there are some disadvantages. So we can take all these stress components as a function of time, and for every instant in time that we have digitized in our stress history, we can use the von Mises stress formula to calculate an equivalent stress. You know, if you're taking machine design as an undergraduate, maybe even mechanics and materials, you might have talked about the von Mises equivalent stress and how handy that is to determining whether or not something is going to cause yielding in a material or not. So it stands to reason that we might be able to use the same sort of thing in fatigue analysis. All right, well, let's think about the von Mises equation. One issue that we have with it is whatever numbers you plug in automatically become positive numbers for the von Mises stress. So even if you had just a uniaxial sine wave, okay, when you're positive, you get positive numbers, but when you go negative, you end up with positive numbers. The von Mises time history then will look something like this. And so that's a problem, potentially, when we talk about strain amplitudes, or stress amplitudes, and applying this to, say, an SN curve. What do? Now our stress amplitude is half what we think it ought to be based on the original picture for sigma x. Okay, so this is an issue. Some people have overcome this issue, or they like to think they have, by using something called a signed von Mises stress. So let's take this situation where we have this sigma x only. Okay, what does that Moore circle look like? When we're going positive, it starts this way. It gets bigger and bigger and bigger. Okay, then it starts to decrease. It gets smaller and smaller and smaller. Once we get to 0, right here, our Moore circle looks like this. And then it starts to expand on the other side. So it goes negative. As we go down this way, it gets bigger and bigger and bigger, smaller and smaller and smaller. Then it goes back to 0 again, and it starts looking like this picture over here. So what a signed von Mises stress does is it takes the sign of the principal stress with the largest magnitude and puts that into the von Mises. So in that case, then we would get back to having a von Mises stress that has positives and negatives. And we have our time history, and we've recovered our correct stress amplitude that we'd plug into our SN curve, for example. All right, and that sounds like a good idea. Let me show you an example of where this fails. Let's take a look at a particular state of stress that is pure torsion. Just shear stress that we have. It's a time history. This is not an uncommon type of stress situation. Shafts often are subjected to torsion, and maybe torsion alone is the primary stressor. Okay, what does the Moore circle look like in this case? So sigma and tau. Well, the Moore circle for this state of stress is a circle that is centered at the origin on the Moore circle plot. Okay, it's equal on both sides. It gets bigger and smaller as the time history changes. Okay, so you may have a stress history then of shear that goes back and forth in time. You may be able to compute a von Mises stress, but what sign do you associate with it? The principal stresses are always going to have the same magnitude. So assigned von Mises is not always going to work for you, even in proportional loading. Okay, so be real careful with that. And I only teach this because I've seen this kind of out in the wild. People do have this option sometimes in fatigue analysis software to do assigned von Mises fatigue stress, fatigue calculation. And generally, I think you want to avoid it unless you are very careful and understand some of the pitfalls are with using the assigned von Mises. Non-proportional loading has its own can of worms that come into this as well. But even for proportional loading, it is usually a better thing than assigned von Mises. So you might say, well, why don't we just use the principal stresses? And you could use principal stresses. You can use the time history of the first principal stress if you'd like. But again, in situations where you have pure shear, you get into this kind of weird issue that we have here. Let me make a new slide for principal stresses. All right, so you could also use time history of principal stresses, and there are similar issues. So again, if we were to take a look at a stress block, maybe with sigma x, sigma y, and tau xy on it, and we were to think about the Mohr circle, I usually plot positive tau on the bottom. If we have some proportional loading, then the circle just, the circle changes radius, but the principal stress directions remain the same. That might be a way to use a time history of, say, your first principal stress. But again, if you go back to pure torsion, then you still have this issue of, you know, which one really is sigma p1? Is sigma p1 always defined as your positive stress? And then you have this kind of clipping waveform again. So again, I would tend to avoid principal stress calculations when you have multiaxial histories like this. Now you can do the same sort of thing with strains, and the same rationale applies as to why you probably don't want to use a signed von Mises strain type term or a strain history based on principal strains. There are some issues with that. And so we're going to talk about the critical plane approach in an upcoming video lecture. That's the one that I tend to recommend. Now there are some other multi-axial type calculations, Dang-Van and so forth, that have arisen since the critical plane approach, but from a pedagogical perspective, from a perspective of what goes on from the materials point of view, I think the critical plane approach is a really solid approach to use. And so we'll get into those details in, like I said, in an upcoming lecture.